Today we will start the second topic of this course, which is kinematics of particles, right? So this course have two different parts. One is dynamics of particles and then dynamics of rigid bodies. And in each of those parts, we will be discussing two main topics, which will be kinematics and kinetics, right? So today we'll start the first of that topic, dynamics of particles, and in that we will be discussing kinematics of particles. In this particular chapter or topic, we will be discussing first rectilinear motion, which is the learning objective for today's session, and then in next sessions we will be discussing curvilinear motion and then different coordinate systems. So kinematics, we know already that it is the study of geometry of motion without reference to the actual force which produced that motion. Before actually I start, I want to acknowledge that the training material I am using in these slides is mostly taken from this textbook. So my objective for today will be to discuss rectilinear motion. I will define what rectilinear motion is, and then in later parts of these sessions we will be discussing curvilinear motion, different types of coordinate system, and some other topics in kinematics of particles. So first things first, we are here discussing kinematics, and that is actually the study of geometry of motion. So for example, motion paths, velocity, acceleration, their values, trajectories of particles in certain particular types of motion, all that will be discussed in this part. So this is geometry of motion, right? The applications for this topic in practical field mostly are related to, for example, design of machine components, where you have certain parts moving along a certain direction or certain line. So for example, design of machine parts, sometimes several machine parts are designed to move in a fixed path, right, as part of a big assembly, and then you are required to determine the velocity and acceleration and some other motion characteristics of that object or particle, right? So you might not reference the forces which are acting on that particular part, but you will be interested in the motion or path of that object. So for example, design of machine parts like gears, for example cams, and certain other applications in mechanical engineering, aerospace engineering, and manufacturing engineering. Similarly, for example, flight trajectories, calculation for altitudes, velocities, accelerations, path of a spacecraft and airplane, for example. So all those calculations problems will be in this category. So it has a big application in determining that flight trajectories. Similarly, the rocket movements or rocket trajectories. And you can also think of several other applications where a certain object or particle is moving in a certain path, and you are interested in calculating its velocity, acceleration, and some other parameters without reference to the force which is actually producing that motion, right? So we will be discussing some of the numerical problems that will also highlight the applications of this topic. You will be seeing several real examples with some real numbers, and you can then get an idea that how powerful that science is. There is sometimes a classification of particle motion called constrained versus unconstrained. So as the name indicates, that constrained particle motion means that the path is fixed already and particle will follow that path, right? Again, you can imagine that a certain part of a big machine which is designed to move in a particular path to fulfill some particular function, right? So that will be a constrained motion. When I say particle, I again would clear that it doesn't mean that the object is a small object. It simply means that I assume it to be a particle, that its dimensions are not relevant to the problem we are studying, right? So when I say particle, it can be a real object, but its dimensions will not be relevant to the problem we are studying. So for the purpose of that problem, we can assume it to be a particle. So constrained motion is when the path is fixed, right? So you force a particle to move in a fixed path for a particular purpose or application. Unconstrained means that the particle is free to move in any path, right? So if, for example, there is a point A in a particular frame of reference, and if there is only one path available to reach to a point B for a particle, then we can call that motion as constrained motion. But if the particle is free to select any path to reach to point B, then it will be unconstrained motion, right? So we should keep that classification also in mind. So now let's assume that how many ways are available in which we can determine or define the position of a particle in space, right? Three-dimensional space. So for example, this plane projection which you are seeing right now is representing a three-dimensional space, and there is a particle here somewhere at a location P, right? So the first way to define the position of this particle with respect to a reference point somewhere, let's say located here, let's denote that reference point as O, right? So the first way to define the position of P with respect to O is the rectangular coordinate system, which means that you have three translational axes. So let's represent them as like X, Y and Z, right? And the first way is called a rectangular or Cartesian coordinate system, that you tell that, for example, move first some distance along x-axis. So for example, let's say I say this is some x distance along x-axis. So I reach from O to somewhere here, then some distance along y-axis. So I move like from here and reach somewhere here on this xy plane, right? So this xy plane is actually the floor of that three-dimensional space. So this is the floor of that three-dimensional space. So you move some distance x translationally, and similarly move along y for some distance. Let's call that distance as small y. And then finally move up along the third axis, which is, let's say, this height, and that is z, small z. So by knowing these three numbers, small x, small y and small z, you will actually reach to this point P, right? So the first way to represent the location of this point P is using Cartesian coordinate system, and that will be actually a triplet of x, y and z values, how much you should move along x, how much you should move along y and then along z to reach to that point, right? All three movements will be translational, right? So this is the first way or most convenient way to represent the location of a particle P. This is rectangular coordinate system, which we use in several daily applications in different types of problems. So rectangular coordinate system, right? Now there can be a second way also that you can reach to that point P, and that is using another set of three numbers, not x, y and z, but another set. For example, Let's say that I start from origin again, but instead of moving along x and then along y, I move in a diagonal direction in xy plane, which is the floor of this three-dimensional space. So I move on that floor and reach to a particular point, and that length which I cover on that floor, let's represent it with small r, right? Let's represent the angle which that path which I moved with the x-axis, let's represent that angle with theta, right? So what I did now, instead of moving along x and then y and then z, I moved in xy plane in a diagonal direction, and I moved a distance equal to small r, right? And that small r path was making an angle theta with x-axis, right? And then again from that point I can move up in z-axis by a distance small z and reach to the same point again, right? If I follow this path, I will be actually requiring another set of three numbers, and those three numbers now will be small r, theta, and then z again, right? Small r will be my length which I follow like in a kind of a diagonal manner in xy plane, and that small r will be making an angle theta with x-axis. So I should know theta because there can be infinite small r paths, but I should select the one which makes an angle theta, and then again move up in z-axis just like the translational rectangular coordinate axis, right? So if I know these three numbers r, theta and z, I can reach to the same point again, right? Instead of using x, y and z, I can use r, theta and z to reach to that point again. If I am actually doing that, I am using what we call as the cylindrical coordinate system. So it is no more the Cartesian coordinate but cylindrical coordinate system. So that will be a second way to reach to a certain point or define the position of a point in three-dimensional space. But now there can be a third way also, and that is that, for example, I again start from origin and I directly join origin with the point P. So let me just write like this. So that vector which actually will be joining origin with directly the final point in 3D space, that will actually be a three-dimensional vector, right? Let's represent it with capital R, right? So if, for example, you drop a shadow of this capital R on the xy plane, that will be actually small r, right? So small r is actually the shadow of that capital R on xy plane, the projection of that capital R on xy plane. All are clear on this, right? So now if, for example, you know capital R, you know theta, and you know another angle which is an angle between small r and capital R. So let me represent that with like this. Let me represent that angle with a new angle symbol called phi, right? So now what you know, for example, capital R, theta and phi, right? These three numbers can also take you finally to the same point. So you can reach to the same point P using these three numbers also, right? If you are doing so, you will be actually using what we call as spherical coordinate system. So that will be actually capital R, theta and phi, right? Again, I would define capital R is representing a three-dimensional vector connecting origin to your final point in space. Theta is the angle which the projection of that capital R is making with x-axis, and phi is the angle between that projection and that three-dimensional space. So imagine that small r is a shadow of capital R, and that shadow is making a vertical angle with its original capital R vector, and that angle is actually represented here as phi, right? So you can reach to the same point using this triplet also. So x, y, z translational motions, r, theta, z. Now r is a translational motion, but theta is rotation, and then z is again translational motion. Here again two angles and one r vector, which is a three-dimensional vector. That actually will be spherical coordinates. So spherical coordinate system. Now the question should be that in which cases we should use Cartesian coordinate system, in which cases we should use cylindrical coordinate system. So the answer would be that it will depend on the type of problem we are studying, right? If for example we are dealing with motions which are mostly translational, an object is moving in one direction and another direction, so it is more convenient to represent that motion or define the position of particles at any time instant t using rectangular coordinate system, right? So for example, if an object is moving in x axis, then y axis, then z axis, right? So or it's moving both in x and y axis at the same time, like in a curved path. So it will be more convenient to represent the location of different points on that path in rectangular coordinate system, right? But for example, if you are dealing with circular motions, an object is like rotating in circle, right? And you are required to determine the motion characteristics like velocity, acceleration at this point, then at this point, and then when it was somewhere here. It will be more convenient if you use a polar coordinate system or cylindrical coordinate system. So for example, you assume the origin in the center, and then the angle can represent, theta can represent the position, and the length of that vector r can represent the position of that object more conveniently compared to if you were using a rectangular coordinate system x, y, right? Similarly, if the motion is in like complex helical paths, like curvilinear motion in three-dimensional space, like an object is moving in like in circles, but at the same time translating also, very complex motion, use of spherical coordinates may be more convenient, right? This was all about motion, but we also decide about which coordinate system to be used, even sometimes in statics also. For example, I am from civil engineering, so I can give one common example, that for example, most of the buildings, you know, they are rectangular in shape. For some reason we decided to build them rectangular all along. So for example, if you see the plan view of a building, it mostly will be like a rectangle, right? All the walls and beams and columns and all the components in a building, they will be like mostly 90 degrees, making 90 degrees with each other. So if a building is like a rectangular shape and all the components are either parallel to or perpendicular to that main or minor direction, so a rectangular axis xy will be more convenient obviously to be used to define the location of, for example, corner points of a building or any object within that plan, because it will be either aligning in this direction or aligning in this direction, right? If a wall will always be aligning towards main side or minor side. But there can be certain buildings which are circular in nature, their structure is circular, like for example large stadiums or some other buildings also which are having a circular plan, and they may have some specific arrangement of walls, like all the walls are like pointing towards center like this, right? And certainly maybe some can have curved walls around a circle, like large auditoriums or playgrounds, right, indoor fields and all that. In all that we use mainly the cylindrical coordinate system, because all of the geometries are circular and therefore we can easily define their location using how far they are from origin, which is generally located in the middle, so which means small r, and then their span can be represented by the angle theta, that how large or small they are, right? So it may be more convenient to use cylindrical coordinates to represent the location of different objects in a circular type of a problem, right? Same is applicable for motions, right? We will use that in the context of motions here in this course. So that was a prerequisite concept. Before we actually start this, we have three types of coordinate systems. So we should know that they all are suitable in certain problems. Mostly we will be using Cartesian or rectangular coordinate system, but you should know that there are other two ways also. So just to summarize that whole discussion, for example, if we have a particle P here, which is moving from A to B, right? So first of all, that motion can be either constrained or unconstrained. Secondly, that the position location of this point P can be actually described either using rectangular coordinate system. So you move, for example, from here and along x-axis equal to a distance x, you reach here. Then you move along y-axis equal to a distance y, you reach here. Now that point is on the floor of that three-dimensional space, and then you move up and up with a distance small z and reach to that point P, right? Cylindrical coordinate system, in which you require actually to move from origin in a direction along that 2D plane, which is the floor of that 3D space, with a distance r, and that path should make an angle theta with x-axis, right? So you should know the length of r and the angle with the angle which it is making with one of the axes, for example x-axis and theta, and then from there you exactly go up with the same distance z to reach to the same point P again. Finally, spherical coordinate, capital R, theta and phi. Capital R is a three-dimensional vector connecting origin and the point P, and its projection on the floor will be small r. So if we know capital R length of capital R, if we know small theta, which the small r is making with one of the axes, and if we know another angle called phi, which is the angle between small r and capital R, so it's like a angle in vertical direction between the shadow of capital R and the capital R itself. So that phi also need to be known. So if you know this triplet, you again can be able to reach to the same point, right? So finally, the motion of that particle P can also be described by another pair of measurements, and they are called normal tangential measurements, NT, right? For example, if you take a tangent of the path of that motion at point P, you will be having this line, tangent, and perpendicular to tangent will be a line called normal, right? So at any time instant, you can also provide the measurements along t and n axis to describe the motion of that object, right? Because as the P is moving, the tangent and normal are continuously changing, right? So if you know the information about tangent and normal at different time instants, you can actually know the motion of that object, right? So while the first three will be used to describe the location of a particular object, you can also use the normal and tangential measurements to describe the motion at any time instant, right? So for example, at this particular time instant where P is here, you can determine this number and this number. You can tell what the tangent is, what the normal is, and then it will be changing at the next time instant. You can come up with a new pair, and then in the next time instant another pair. So if you know t and n at all time instants, you actually know the path, right? So the path can also be described in terms of tangential or normal measurements. That is another way to describe the motion of particle P. The reference frame which we are using here to define the location of a particular point can be absolute or can also be in relative motion, right? So this whole reference plane, this whole space we are assuming in this figure can be stationary, or it can also be moving with respect to another reference frame, right? In that case, it will be having a relative motion, right? So you may be experiencing a problem where your own reference plane will be having some relative motion. So that was just an introduction before we actually start the rectilinear motion, which is our first topic in this chapter. So the most general case which we have just seen is actually three-dimensional kinematics or three-dimensional kinematic motion, right? So here you will have 3D motions, but we can also simplify it and first consider a case of two-dimensional motions, right? So two-dimensional motions will be actually a subset of the more general case, which is 3D motion. So we can first consider a case where the motion is only happening on that floor, on that XY plane, for example, right? That will be a simpler case compared to directly going to 3D motion. But there can be a further simplification also, and that is we can assume that the particle is only moving in one line, right? So motion in one line, motion along only one line, one straight line. If we can consider that case, that will be even simpler than 2D motion, right? A case of curvilinear motion will actually be a real case of 2D motion. So if, for example, a particle is moving in that floor, XY floor, for example, now I can draw it like this. If it is moving in a curved path from point A to B, it is actually simultaneously moving along X and Y at the same time, right? So it is a curvilinear 2D motion, a slightly more complex case. But what we will be discussing in today's session is a more simpler case that it is a motion along only one straight line. So that is actually called rectilinear motion. Rectilinear motion means a motion along only one line. So for example, if you assume that this is the origin point, right, the motion can only happen or occur towards right or towards left of that point, right? So there is no second axis involved even in this case, the most simple case, right? So the direction of this rectilinear motion can only be towards right or towards left along the same line which it can move, right? So we can have one origin and can call rightward motion, for example, as positive and leftward as negative, and therefore we will not be requiring vector notation to represent this motion, because vector notation will mainly be used when you have motion along both x and y. Now you are currently having a case where motion can only happen along one axis, right? We can simply use algebraic equation symbols plus and minus to represent the direction, right? So there can be only two directions in this rectilinear motion, either towards left hand side or towards right hand side, or in other words, either negative or positive, right? But for describing a motion which is simultaneously in both axes, like curvilinear motion, for example, this case, you now need a vector notation because every time instant the direction is now changing, right? And the path is also changing, right? So therefore you need vector notation to tell the direction at any particular time instant. But for rectilinear motion we will not be using vector notation, we will simply be calling the motion or displacement as positive or negative with one sign notation, that maybe rightward motion can be described by a positive sign while the leftward motion can be described by a negative sign. So we are currently here. In the next class we will be moving to a more complex case, which is curvilinear motion, right? And finally we will be able to actually discuss the three-dimensional motion, which is the most comprehensive case where the motion is occurring in all three axes at the same time, right?